It's really my pleasure to introduce Jeannette Bohg, which I'm sure many of you know. Jeannette is really at the core of the topic of this workshop. She's been working on how to get robots to learn these manipulation skills. She has taken the problem from many different perspectives, from already trying to learn all this visual, tactile information and how to transfer that into actions, but also how to do a hierarchical set of actions, also looking just at grasping, which is still a solved problem in some cases, not solved in other cases. And once you have the object in your hand, how to manipulate it. So I'll stop here and I'll give the floor to Jeannette. Thank you.
Thank you very much, Aude, for introducing me, and thank you to both of you for organizing this and inviting me. It's a very exciting workshop. I'm glad I could make it in the end and all this resolved. So I changed my title a little bit to include two human learning principles, although in the beginning I thought I would just talk about one. So let's get started to talk about scaffolding and imitation learning. Okay, I'm in the wrong window apparently. Okay. So the premise of this workshop is that humans are incredibly good at any manipulation task, right? And that it's fairly unclear what these principles exactly are that allow this kind of robustness and dexterity, both in execution and in learning, actually. And it's even more unclear how these principles can even be transferred to robots that have a completely different embodiment and completely different kind of characteristics of sensing and actuations. So the questions that were posed by these workshops where kind of like, how do humans achieve such manual dexterity in all these tasks? What kind of learning curricula can shape these skills? And can some of these strategies be transferred to to robots? So yeah, that's really what I would love to talk about, except for this one, I don't really know. So Dagmar is going to talk about this after my talk, I believe. I'm looking forward to that. So I'm not going to talk about this. I'm going to talk about two principles that I think are very common in human learning, which are, first of all, scaffolding. So here just showing an example of learning how to ride a bicycle, maybe using training wheels, or learning by or from demonstration here in a cooking task where someone is showing how to make a pancake and the little boy is just repeating this. So related to these two principles, I want to talk about two example projects that we've been recently working on in my lab chair, the one on scaffolding, and another one about learning manipulation concepts from verbal instructions and human demonstrations. Let me start with the first one. On scaffolding, and anyone who has ever worked with a robot knows that they are completely clumsy, as was also mentioned on the workshop website. So here are just 3 example tasks where the robot is trying to learn how to do these and is pretty terrible at this in the beginning and needs a lot of trials to even figure out how to do this. So peg insertion, a wrench manipulation task, and shallow depth insertion. And what many people have actually figured out is that humans in the robotics community, amongst others actually, that humans leverage a lot the environment to ease some tasks. So this can be scaffolds to actually build buildings and reach certain heights and areas. Or as I showed already, it can be parents using training wheels or other means to actually teach kids new tasks or new skills. Or in industry, fixtures are actually used to help the manufacturing process. So what we were wondering in this project is really, can a robot exploit this principle specifically for learning? And an example here is an example, we just take this peg insertion task that is pretty hard for a robot to do. But if you actually place a fixture that is well aligned with this hole in this case, the task actually becomes quite easy, not only to execute, but also to learn, because this fixture really blocks the wrong motions that are not leading to task success, and therefore kind of forms a funnel that restricts the motion of the robot and guides the robot towards successfully inserting this task. So that robots benefit from these contact constraints has been shown to work also for robots by other people, among others by 2 speakers who have already spoken today at the workshop. So I just leave you with these citations. However, what we wanted to explore is really how environmental constraints can also help to ease learning of a manipulation skill. So a slightly different goal. And specifically here, we are interested in the problem of how can a robot autonomously discover how to best place this fixture and therefore help the other robot that is learning this skill to actually execute the peg insertion. And our approach here is that we have an inner and outer loop where the outer loop learns to place the physical fixture. So you see here on the left, one of the robots, and the inner loop learns the manipulation skill. And then after a fixed amount of time, it returns a reward to the outer loop. Therefore, this is the reward for the outer loop to learn to better place this fixture. So the inner loop is not super interesting. It's just like an off-the-shelf model-free RL algorithm. We're actually using A3C. It's not so important. What is more interesting and new about this work is this outer loop that we formulated as a contextual bandit. And really, the goal is here to learn a good policy for choosing an action, so placing this fixture given the context, which in this case is the depth image. So again, like we have the context of this particular manipulation object. We want to find the best fixture, and we formulate it as the contextual bandit problem. The challenging part about this particular problem for a bandit, for multi-arm bandit, is that we have to deal with a discontinuous Q-function, actually. Let me talk a little bit about this. So we approximate the Q-function. We're trying to learn the real Q-function with this, or approximate it with this QW. This returns basically the expected reward after taking an action A, with a depth image as a context, here denoted as S for the depth image and A for the action. So once we have this approximation, we can use it as test time just to basically output the action that, given the context, that returns maximum reward, and then execute this one. And as I mentioned, the problem here is that this Q function that we're trying to approximate is actually discontinuous. So this is kind of how it looks like. So on the y-axis, you have the reward, and on the x-axis, you have displacement of the fixture. And you see on the left here, which I don't know if you're actually going to see my mouse. On the left, you actually see the fixture covering the hole, so the robot will never be successful. It will never get a reward. And then suddenly, when the fixture is correctly aligned with the hole, it will get maximum reward, and this reward will decrease if the fixture is somewhat suboptimally aligned. So we have a discontinuity here. And one of the contributions of this paper is actually a new algorithm for learning this kind of discontinuous Q function. Sorry, was there a question? There's some noise in the background. Sounds like a different language. Okay.
I will try to unmute that, but it's hard to see who is speaking. Yeah.
All right, no worries. So we have a new algorithm also that is learning this discontinuous Q function. In the interest of time, since there were some delays right now, I'm just gonna skip over this. Feel free to check it out in the paper. And let me just skip over this, but the point is that we have a new smooth zooming algorithm that basically learns this function in a good way. All right, so coming back, this was the outer loop. Coming back to the inner loop, as I said, it's like not very interesting. It's basically given an RGB image, it runs the model-free RL algorithm to output the optimal action. And here's one important thing though to know. If the fixture for this particular manipulation task is placed optimally, then also this inner loop model-free RL algorithm learns faster to do this task. So pay attention maybe to the top left graph where you see a learning curve. So we want this to be getting high fast. And in orange, you see the reward, or basically a learning curve when the fixture is optimally placed, and in blue when there is no fixture. And by the way, in purple is the learning curve when the fixture is not optimally placed. And we see kind of similar learning curve behaviors also for the other two tasks that we investigated in this work. So just to summarize, putting it all together basically, the faster, we have here the outer loop that does the fixture post selection with one robot, and that when optimally placed, the inner loop can basically learn a manipulation skill faster. And the faster the inner loop learns, the higher the reward for the outer loop robot. So since I have talked about this Q map, and how it is learned, I will just show you how this, or visualize this here for you again to give you an idea of how this looks like. So the outer loop action for this particular case is really three-dimensional. So you have the placement of this fixture just translating in the plane XY direction, and it has also particular orientation. And here on the bottom, you see basically three different cases for three different orientations with slightly translated positions of the fixture. And on the top you have the Q map where each pixel basically corresponds to one position of this fixture, and the darker the pixel, the more reward the robot gets, basically for placing this fixture in this way. So and you see the maximum value there corresponds to the placement where this fixture is really aligning with the corners well of this hole, and so it constrains the motion of this inner loop robot. Okay, so just to show you how this looks like, I'm playing here this video for you. So you see the robot, the outer loop robot is basically running Qt opt right now. So basically sampling a bunch of positions, finds the best one, and then we are replaying the policy that was learned from the outer loop. Here's another task, which is the wrench task. Again, the outer loop robot tries to find the best pose and then helps the inner loop robot to do this task in the best possible way. And here's another pretty difficult task, which is used for inserting batteries into cell phones. It's called shallow depth insertion. And again, the outer loop robot placed the fixture in the best possible way so that the inner loop robot can actually do the manipulation task in an easier way. All right. What we also found is that once we have learned this policy for placing the fixture, both policies basically generalize to different peg shapes as well. So this is really just running the same policies for both inner and outer loop, and it just works, which is really encouraging to see. So just to summarize this particular part of the talk, so the paper that I just talked about is actually going to be presented at ICRA, so feel free to join the Slack channel for this paper. And the main idea here was to allow a robot to learn to place a fixture to funnel uncertainty for the robot that actually has to do the manipulation task. And we had an algorithmic contribution that I didn't actually talk about that much, which is a smooth zooming algorithm for learning a discontinuous Q-function. And the result is that the learning for the inner loop robot is dramatically sped up if the fixture is placed optimally. So if you want to know more about this work, Lynn and Toki are in the Slack channel, so you can join that one and ask them all the detailed questions you're interested in. All right, so I mentioned that I wanted to talk about two principles that we find in humans when they try to learn a new skill. And this part of the talk was about scaffolding. And now I want to talk about the second principle, which is learning from demonstration. Again, in this, or as an example work from our lab on this particular concept, I'm going to talk about this work on learning manipulation concepts from verbal instructions and human demonstrations. So what is the problem definition here of the problem that we want to solve? Basically, we want to equip the robot with a set of manipulation concepts that take in verbal instructions, like for example, the ones you see here, and a scene image of how the scene looks like before the robot starts even doing something. And we then want the robot to correctly execute the action according to these verbal instructions. And of course, this is a very hard thing to do, to equip a robot with these actions. And machine learning would, or the hope is that machine learning would provide us with a way to let the robot automatically learn these action concepts. But the problem is, of course, like, how do we provide the supervision to really scale this up? Of course, one way on how to do this is to learn from human demonstration, because if you learn from human demonstrations, there are several advantages with this. You don't have to do any kind of reward engineering as you have to do for reinforcement learning. And if you're going to use a video, you can also avoid demonstration techniques, like, for example, teleoperation or kinesthetic teaching, that are also can become somewhat tedious, especially if you want to demonstrate a lot of tasks, a lot of different tasks. So the problem, of course, with learning from human, especially from video demonstrations, is that there is a large domain gap between what the person is doing, or how the video even looks like, compared to what the robot is doing. So here I'm just showing you 4 videos of what a human is doing when they are asked to close something. And you see, like, the objects are, for example, very different. The videos look very different. And on the right side, you see the robot actually closing a drawer. So this is a pretty large domain gap, and the verb close something, or close, actually changes meaning when applied to different objects as well. So what we want you to do in this work is to develop a new learning from visual demonstration method to teach the robot still this concept of closing something. And here's the main idea that we're following in this work. We are basically letting the robot execute its action, and then ask an action classifier that is learned on human videos to also score the robot video. And this classification value, or basically the probability of the robot video looking like the robot is closing something, provides a reward to the policy that the robot is trying to learn. So basically that was our idea. And of course we wanted to know if we can bridge this domain gap. As a data set, we actually found this data set called the 20 billion something data set in version 2, which is very interesting because it has hundreds, thousands of images of people doing a certain action. And these actions or these videos are actually annotated with natural language instructions. So this gave us basically the material to have a robot learn from human video demonstrations. So from these many, I think it's 140 tasks in the 20 billion something data set, we selected 78 that actually could be simulated for a robot and made sense for a robot. And we wrote the simulation environment that we used for the robot to actually execute these tasks. And the first step we did towards letting the robot learn these 78 tasks is to just have it learn one task at a time. So here, the goal is to learn the single task manipulation concept. Again, the input is a scene image and an instruction. And as an output, we want the robot to actually execute this task in the scene. And this is how the architecture actually looks like. So again, the input is the instruction and the scene image. For the natural language instruction, we use just an off-the-shelf model BERT, and also for the image, an off-the-shelf model ResNet. In this case, we concatenate these 2 inputs as a low-dimensional feature, which then feeds into a network that generates actually a policy. In our case, we are generating a goalpost for the robot end effector and a forcing term that basically shapes this trajectory. So note that we are right now not learning yet a feedback policy. We are really learning like one policy that is for now executed open loop. So kind of this is also like a Bandit problem almost. And then the robot executes this task according to the output policy. It generates actually an image sequence, so a video of how this looks like. And we asked the action classifier that was trained on the 20 billion something something data set to classify this video on whether it actually does close something. So that's the overall idea, and it really follows this paradigm of watch, listen, and imitate. And this actually worked really well for the single task learning. But our goal, again, to remind you, was to have a multitask learning environment where we can input even novel instruction and the robot would do the right thing given a certain scene image. So how do we get to this multitask policy? Again, we now have single task expert that were learned using this video classifier, as I explained before. So here are just some examples of these. And then we actually use these single task experts as demonstrators for the multitask policy. So we learned the multitask policy by just imitating the single task experts all at the same time. So in the bottom, you basically see the convergence of the multitask policy trajectories to one dimension, in this case, of the actual single task expert trajectory. And you see like some tasks are harder to learn than others. And where we end up with this is actually a method that can take in, again, these scene images. Here you see and follow some given instructions. Here you see the instruction closing something. And it can actually be executed under varying poses of this draw in this case. Here's another example of where the instruction is to pour something into something. And again, the note that the poses of this container are basically different in the start pose as well. And so we have learned basically many of these kinds of tasks that are now all combined into a multitask policy. So here again, just some examples of the 78 tasks that we learned. And also I want to mention like some of these are actually harder to learn than others. So there's still a lot of work to be done there as well.
2 minutes left,
also,
Jeannette. 2 minutes
Two
left.
minutes left? Yeah,
yes,
I'm almost
thanks.
done. Thank you. We also can show generalization to novel instructions. So you remember we have this multitask policy. And here we input somewhat maybe grammatically not like perfect examples of instructions. And the robot actually does something reasonable that roughly corresponds to these novel instructions as well, which is encouraging to see. So just to summarize this part, the main idea of this work is really to learn to imitate humans using video activity classifiers to provide the reward. That's basically this goal, and the algorithmic contribution is the curriculum learning approach of multitask policies from instructions and video demonstrations. So the result of this is that we achieved a multitask policy that can execute 76 tasks that are indexed by natural language instructions, and it can also use novel instructions as input and actually execute reasonable actions. So this work is not yet on archive, but it will be soon, including also the database and the simulation environment. It's going to appear at RSS. And if you are interested in that work, you can just go to the same channel from the first work, because the same authors are actually on the paper. You can just bug them about that. So yeah, just to recap the talks, I presented 2 example projects from our lab, where one was on basically allowing one robot to place fixtures to help the other robot to learn a manipulation task faster by exploiting its environmental constraints. The second work was on equipping a robot with manipulation concepts that are basically mapping verbal instructions to robot motor skills. And thereby we kind of instantiated these two principles that we observe in human learning, scaffolding, and learning from demonstrations. And just to remind you, these were the two questions posed by the workshop. Which are very interesting, and I hope I give like some answers to them. And I want to make a very quick plug. So I'm co-organizing actually a new seminar that is also public, together with Alberto Rodriguez, Luca Colonna, and Marco Pavone. And actually this Friday, we're gonna have Alison Okamura speak, and the Friday before that, it was Leslie Cabling. There are like thousands of people tuning in, and you're very invited to also join. So thank you very much for your attention, and I'm really looking forward to your questions.